this it from in functions. This is good. Right. Okay. We wait 1 more minute. Some people are still coming. Yeah. Let's see. Yeah. My cell phone is also there recording, so I cannot make pictures now. But let's wait.
360 pictures in the afternoon where we are going there. Also from here, what do you believe?
How many pictures?
No, one picture 360 degrees.
Okay, yeah, this would be nice.
Because I have
Or we have Lamberto, I will make one pause. Okay. Then we can make it maybe after this. Yeah. Yeah. Yeah, it's fine. It's fine.
And the paparazzi.
Yeah, please. Someone has to be the responsible person.
This media obsessed world.
Yeah, exactly. Yeah. Okay, I unpause it, resume, and like this. Okay. So, welcome everyone. Thank you for coming. This will be the second lecture within this project called AURALIZE, and my name is Kristian Jambrošić. Most of you know me since you are students of this institution, but we have also some guests. So, with me is also the second lecturer, Professor Lamberto Tronchi, who will have his lecture after mine, starting at 12:15. So I will make a short introduction first to the project. So this AURALIZE Erasmus Plus project is a mutual project of the Consorzio Futura in Ricerca from Italy and University of Bologna, who are the lead partners, and our university as the partner in this project. It will end of October this year, and we have certain objectives, and one of them, the most important, is to make some we call it innovative vocational training course in room acoustics and oralization. So this is the focus of our project and also of today's lectures. And we would like to make some, give some experience to the participants on how to do acoustic measurements and how to do oralization, both for students and also professionals. So, this is what we would like to do, and also, of course, some bounding between our institutions, and to have some future projects, hopefully, as well. This is, just the overview of the project, but maybe more important, what we had until now. We had one online lecture last month that is available on the project website. And then we will have today 2 lectures on the fundamentals of room acoustics and on the equipment and methods of recording of acoustic measurements, etc., which you will be able to hear a little bit later. Tomorrow and the day after tomorrow, we have some measurements in situ in our most famous concert halls in Zagreb. This is the Vatroslav Lisinski concert halls and Croatian National Theatre here in front of this building. And then 2 weeks later, we will do also some measurements in Italy, in the theater in Faenza, and in 3 weeks' time, we will do another set of lectures again here in Zagreb. So you're also all welcome to participate on 5th of May to hear the conclusion of this whole travel through acoustics and auralization. What is prepared for this first lecture? It's giving you some fundamentals of room acoustics, and this will be the subtopics I will try to cover. I will give an answer. I'll try to give an answer. What is architectural acoustics? Give you some basic concepts in acoustics. and then speak a little bit more about some of the elements that are important for the sound spreading in space, which are reflection, absorption, and scattering. Then we think a little bit about how rooms respond to sound and how the room volume and shape influences what we call room acoustics. We will talk about acoustic elements, about some parameters that define acoustics, first reverberation time and some other ones. I will mention a little bit about an optimum or optimal acoustic design, and we'll speak about typical defects when designing room acoustics. So let's start with this. The first question would be, okay, we are dealing with architectural acoustics. What is it? And it's usually divided in two main parts, in room acoustics and building acoustics. And it's a little bit easier to explain what it is with some, well, pictures. And one of them shows a nice room where people are happy listening to music. And room acoustics studies actually the sound coming within a room and influencing the same room. So the listeners and the source are in the same space. But then building acoustics studies more how this sound propagates in other rooms, in other spaces within the building. So it's more about sound insulation of the elements of the building. And it already shows that it's important about the perspective. So we study both room acoustics and building acoustics, looking what is the perspective of our study. And in some case, you can see that the same sound can be very enjoyable to one group, like music, but can be disturbing and annoying to the other people, like trying to sleep in another room. Our idea is to go more into room acoustics, where we measure actually the sound quality of a room by examining frequency-dependent and time-varying sound pressure levels within the room and trying to see it through certain parameters. And in building acoustics, as I said, it's more about sound insulation, quality of the rooms, structures in the whole building, and also about background noise levels that exist. Okay, so it is somehow important, all this, that we try to reach and to gain a good integrated acoustic design, because we have a lot of benefits if we think about both room and building acoustics from the start. Because first of all, we will have lower project costs. We will preserve the aesthetics of the interior and exterior, but mostly interior of a room. We will have good user experience, and in the end, there will be less costs if there is some post-construction changes needed. So we strive to reach good acoustics, and it's always a question, what is good acoustics? But maybe this is what it means to us. It means that we will probably, being in rooms with good acoustics, focus better, learn easier, relax better, have less fatigue, maintain our health in the end better, if everything is also acoustically well balanced. Okay. So the basic concepts in acoustics, we could go, of course, very deep with it, and this is not the idea, and we don't have the time. So just a couple of terms that I have to use and usually use when talking about acoustics in general. So it's a science of sound, and the sound is some mechanical disturbance from a state of equilibrium of the medium where the sound spreads. And we are interested, especially where we live. We live in a gas. It's called air, of course, a mixture of the different gases. And what we can experience is a disturbance in the sound pressure, or the air pressure, actually. The velocity of the elements of the air, which are molecules, change of temperature, and change of density of the medium. So this is what we can observe objectively, and some of these also properly measure. And here is just an overview of these physical quantities I mentioned, with a typical symbol and the typical unit we use when thinking about sound in space. Some other ones. So speed of sound is also very important when thinking about acoustics and room acoustics. It's denoted with the letter C. We measure it in meters per second, and the typical speed of sound at 20 degrees centigrade, which is the usual room temperature and in rooms we live. So it's not that dependent on the time of the year. It's about 343 meters per second. So it's fast, but not that fast. We sometimes have to really think about the proper speed of sound. And then again, we also care about the frequency of the disturbance. So the frequency of the sound, and it's also denoted with the letter F and measured in hertz. So when we have both parameters, then we can talk also about wavelength. These are all, of course, very common and very used parameters. So the wavelength of a sound wave is actually the distance between wave shapes that repeat. We can have many definitions. This is one of them. And it's just calculated in a simple way by dividing the speed of sound with the frequency of sound. And then we actually get what is important to us as people. We are a certain hearing range. So, and this is what we focus to. And our hearing range ranges between 20 hertz and 20,000 hertz, which means that we hear all these disturbances in sound if it occur at least 20 times per second, up to about 20,000 times per second. And then we get wavelength of the sound somewhere between 17 meters and 17 millimeters. And this is also very important because many things we care about in room acoustics are connected with the ratio between the size of different elements in the space with this wavelength. And I will repeat this a little bit later as well. So as mentioned, we do have certain hearing range, and then we usually show these pictures of some hearing area where we can see the hearing sensitivity. So it's obvious, and we know it also from before, that our hearing is not equally sensitive to all these frequencies I mentioned. At lower frequencies, we are much less sensitive. Or in other words, we need much more sound level to experience the sound equally loud as at mid frequencies, for example, about a few kilohertz, where our hearing is most sensitive. So we have a certain range, dynamic range, where we experience sound, and depending on the frequency, it is between about -5 dB to about 120 dB, where is the threshold of pain. So this range is what we consider our hearing dynamic range, and as you see, we started to use this decibel unit, which is very common in acoustics, and we always use it. So it's just the level compared to 20 micropascal, which is just a unit we use as a reference sound pressure, as a reference sound pressure of hearing threshold at 1 kilohertz. So we had to pick something, and this is what was chosen for acoustics. And when compared these disturbances in sound pressure, which we hear, and we compare it to the sound pressure, the static one, which we can measure with a barometer, they are very small actually. So we hear the sound pressure in the air is about 100,000 Pascal, 100 kilopascal. But we hear micropascal changes in this pressure up to maybe a couple of Pascal, or maybe 100, not more than this. But what is important that they occur very quickly, between 20,000 times per second. Otherwise, we can have very slow changes, much more than this, but then we don't experience it as sound. It is then below our hearing range. We call it an infrasound, as we call above this range ultrasound. But this is not the focus of our lecture today. Okay. Moreover, thinking about concepts in acoustics, it's very important to think about how certain sound source influences the space around it, and we usually consider point sources. So some elements, like for example, a loudspeaker that emits sound, and it emits all around this object in a way, we call it acoustic monopole, that is shown in this very simplified animation. And I hope it is clear or clearly visible. The red dots represent some molecules in the air, where we can see that near to the sound source, which is in the middle, the molecules move much more with more amplitude, with a larger amplitude, if we compare it to the molecules at further away from the source. So this concept we know before, and this is the so-called inverse square law, where we see that the sound intensity decreases as we go further away from the sound source, from the point sound source. Nothing new, of course, if we are outside and we can experience it well. It's a little bit different in rooms, so I will have to cover this as well, but a very small demonstration just to have some sound examples, not to get too much sleepy during the lectures. I will play back some reference sound level and then 3 more, because we have this law. When you go double the distance from the source, the sound level is dropping around 6 dB. So if we are at 1 meter, then we go to 2 meters, 4 meters, and 8 meters. This is the change in sound level we would experience in a free field when there is no room reflections, as, for example, as we are here now in a room. So let's listen the reference level. It's 1 meter at 2 meters. Four meters. And 8 meters. And back to the reference level. Okay, so we know this, of course, we experience it all the life, and this is nothing new, but it's an important concept in room acoustics, which I will come back to it a little bit later. As I already mentioned, in a field that is not free, where are obstacles, sound reflects. We know this, of course, and then we have a certain specific case when we have a sound source going away from the sound wave going away from the source, but in the same time it's reflected back from some surface, and then we have 2 sound waves going in different directions, and they interact, they add up. And then we get something what we call standing waves. And standing waves are quite special, and we will have to mention them also later, because we have at certain location in space, we have sound pressure level that is very high, and at some it's very low or almost non-existing. So this is what I will come also a little bit later to it. And when showing actually these animations, it's always a question how to represent sound. And we try to represent it very often in this type of lectures. So it's easier to draw just simple lines and like sound beams, similar to light, but in the same time, more realistic would be sound fronts, like we have in these animations, where we represent this difference in the sound pressure or the sound density in the medium. But it's harder to draw it, so we actually use usually both ways to represent. So having this in mind, let's go to the third part, which are 3 particular parameters in sound interaction. These are reflections, absorption, and scattering. So first is reflection. We are well aware of it. So if the sound travels through air and comes to a hard surface, it will reflect. And the incident sound wave will reflect, and then it's called a reflected sound wave. And what we also know, that the angle of incidence is the same or as the angle of reflection compared towards this normal to this plane surface. And if it's 0 degrees, it's called normal incidence. But if the sound wave is traveling along this hard surface, we are calling it grazing incidence. These are just definitions, and we know also it's nothing complicated. In the same time, we can draw it, as I said before, as concentric circles. So this is like more the sound front. And then we can have the sound source with red circles coming to this black line, which is surface it reflects from. And then it is reflected as the blue wave and interacts and comes together in a point where it, as a receiver is, a microphone, or we can be there and listening to the sound. So what is clear is that in this yellow spot or dot, we have an interaction, an addition of the sound source or the sound pressure from the source and from this reflection. And if you look this reflection, it looks like it would come from a place below the surface. So we call it sometimes image source. And this is not a source that really exists behind this hard reflective surface, but it is a concept we often use when thinking about how to simulate acoustics in space. And then this is one way how to do algorithms and programs to calculate the sound behavior with all reflections that exist in a room, for example. Okay. Not all surfaces, the sound wave hits are flat. So there can be in different shapes. Most prominent one could be convex or concave, and they behave differently. So I can show you a small demonstration, which is, I think, quite nice. Shows how it really can change our perception of sound. So here is one small, example where we are looking into how a sound coming from the right person here speaking interacts with the left person, and we are just looking how much the influence of this reflection changes with the way the ceiling is shaped. So if we say one reflection from a straight and plain ceiling is some decibels, which we say is 0 dB, like a reference level. And if we add curvature to be more concave, and we see it like this, then it will start to focus the sound energy towards the other person. And it will, so the reflection level will be higher and higher. And if we go to the very extreme, where it really focuses all this energy from the ceiling to the other person, we have over 20 dB increase of the reflection level. So a lot, really a lot. But then again, if the curvature goes bigger, then the focus is a bit higher, and then it's not that intensive anymore. And if we do it more and more, we can come to some certain spot where again, it's only 0 dB, which will be the same level as the ceiling would be flat. And again, if it's even higher, we can have even lower sound reflection level as before. And if you go in the other direction, so from the straight line to a convex surface, then we will see that the sound level will drop. So we see that these non-even shapes will influence how the sound pressure will be distributed within the room in this very simple example. So also this concept I will mention later on some other parts of this lecture. Okay. Going on, the reflection can be also calculated numerically. We have to have some measure of how much sound is reflected from a surface, because not all surfaces are completely hard and reflective. So we put a very simple relation here is the reflection coefficient, which is the ratio between sound pressure that is reflected from a wall to the sound pressure this is incident. And of course, if everything is reflected, what came to the surface, we have the same number, and then we have actually a value of 1. But when a very little is reflected, or even almost nothing, then the reflected pressure is 0, and 0 over something is 0, and then the ratio falls to 0. So we have this reflection coefficient between 0 and 1, or 0% and 100%. This is very simple, and we need also this ratio a little bit later. And later comes now is the absorption coefficient, which we use more commonly in room acoustics. So it's again a ratio, but an energetic ratio. And we'll look into it as a ratio of energy that is not being reflected, or better to say, which is being absorbed by the surface, to the total energy incoming to a certain surface. And then we use this reflection coefficient to calculate this absorption coefficient as 1 minus R. R can be between 0 and 1, and then also the absorption coefficient can be between 0 and 1. 1 meaning it's 100% absorption of a surface, and 0, there is no absorption at all. And I will show you later, it's very important in many simulations, you really use this absorption coefficient a lot. So Sound absorption is frequency dependent. Actually, everything we speak about in room acoustics is frequency dependent. Reflection and absorption is actually inseparable parts of the same principle. We just call it sometimes reflection, sometimes absorption, but it's the same principle looking from a different angle. And what is also maybe important to mention at this moment, that besides this absorption by surfaces, we have also air absorption in rooms that are part of the mechanism how sound molecules work when interacting between each other and having some friction between them, especially at higher frequencies. At lower frequencies, they are not that important. Here are some examples of the frequency-dependent absorption of different materials. And what we can see that there are hard materials or not that hard materials, and the absorption coefficient, which goes between 0 and 1, at certain frequencies here between 125 Hertz and 4000 Hertz, very common frequencies when we look into room acoustic and room acoustic measures, it's a very big change. For example, the blue line at the bottom is a smooth concrete, very hard material, very low sound absorption. If you use a plasterboard on frame, it's actually also quite hard, but not that much at lower frequencies, and it starts to absorb a little bit, up to maybe 30%, as in this picture, of sound energy. But then if we have, for example, this green one, it's rock wool, so a very porous material. It has very much sound absorption, but again, it's frequency dependent, not so that much at low frequencies because of some also physical underlying principle. And as you see, then certain materials have certain sound absorption depending on the frequency, which we have to know it if we think about how certain material will influence room and room acoustics, and when we have to design it. Okay. And now we come to the third element, which is called scattering, or third parameter. So again, the surface where the sound reflects from doesn't have to be very smooth. It can be rough, slightly, largely, in any shape. So the rougher the surface, the more sound will scatter in directions that are not in the same angle as the incident wave. So they are somehow influencing the sound to go in other directions. So this is a quite important effect. And what is important, again, having in mind the sound wavelength, which is here denoted in lambda and showed like some distance between fronts, the larger this rough parts of the surface and more comparable to this wavelength, the more sound scatters. So we have to always think about, when looking about different unevenness of the surface, at which frequency will it start to interact with the sound and have a larger scattering effect. So we also define a scattering coefficient. It's again quite simple because again it goes between 0 and 1, where 0 means that no energy is scattered in directions different than this specular reflected energy, which is with the same angle as the incident wave. But then some will scatter probably, and all the scattered part is then calculated energetically. So actually the sound scattering coefficient is the ratio between the scattered energy and the total reflected energy. And again, it can be completely scattered, then it's 1 or 100%, or it can be completely 0, so then it's between the same two numbers as before. What are the benefits of scattering? We use it quite often in room acoustics because it increases sound diffusion, which is often very important to us. And it helps in evenly distributing sound energy, which is again a thing we would like to see in room acoustics, and not to have strong reflections. Usually they are not well accepted. And there are certain surfaces that will really provide good scattering, but I will talk a little bit later. What you can see on this graph here is that the scattering coefficients for different surfaces are different in the frequency. A table, which is okay of certain size and has a very flat surface on the top, has some scattering a little bit more on this higher frequency. But if you look at empty chairs or chairs with seated persons, this scattering will go more, and again, it's frequency dependent on higher frequencies. Okay. And I have to mention here also another concept which is connected to sound scattering. It's the sound diffraction, which occurs when the sound wave hits a certain surface, but all these surfaces are not endless. They have some end to it. And at the end of this surface, at the edges, the material will start to do the diffraction of sound occurs. And the diffraction is again directly connected to the ratio between the dimension of the surface, for example, here on the right, the D dimension, with the wavelength. So if it's the wavelength is large compared to the surface dimension, then it will make no, in this example here, no sound shadow, not a strong one at least, behind. And if there is a larger dimension, you will see the sound shadow, but also the diffracted sound spreading around these edges like some new sound sources. It is a concept that is quite important when doing, again, the simulation of room acoustics, because it really changes how the sound behaves in the room according to this diffraction coefficient or diffraction sound. And here again, one demonstration that can help us to see it, how it really influences the sound. So we have a point source and we have a very straight flat panel of 3 meters. And this is the intensity of the sound being reflected from this point source. As expected, the reflection angle is the same as the incident sound angle, and this is what we know from before. But if the frequency of the sound is much higher, let's say 2 kilohertz, then we see that it's again, the angle is more or less the same, but we see some unevenness or some pattern of the sound intensity, and this is because this panel has a length of 3 meters, not unendless. So at the end of this panel, we have this occurrence of sound diffraction, which interacts. There are no new sound waves forming that interact with the incoming, and we get this sound pattern. And this is for a flat panel. If you go again for the low frequency and choose a panel that is not flat, for example, let's say a random pattern of 10 centimeters roughness, we will see a little bit more of sound energy spread, but at low frequencies, it is a very large sound wave compared to this unevenness or this relief. But if we go again to 2 kilohertz, to a higher frequency, we see a much more scattered sound wave. So we see now here the concept of scattering, which we know from before, but before we see also this sound diffusion because of the edges that exist for the pen. So all this has to be taken into account if you would like to have very precise simulation or knowledge on how sound behaves when it interacts with different objects it reflects from. Okay. Sound diffraction is again frequency dependent, and a good example is a sound barrier, which is much less effective at low frequencies. And here we can see an example. We have measured some insulation or how much a sound barrier element can lower the sound pressure from one side. And what is clear to you all, if you have been in front of some wall, if you go behind the wall, you will hear still the sound coming from in front of the wall, if the sound source is there, but with a lower value. So it's not that loud, but it's still audible, usually audible. Frequency a little bit different, but we know this. So we can hear around corners, and we have this diffraction effect always there. The same is also in closed rooms where we have, for example, the orchestra pit, where the musicians are sometimes not visible to the audience, but we have also this diffraction effect, and which allows the sound to reach. Also now, of course, the reflections are important, but also because of the diffraction effect, the audience. So there are many cases where we can experience that this diffraction occurs in real life. Okay, and so we have the basics, the basic terms, and let's see now a little bit more about the room and how it responds to the sound. So when coming to a room, we experience it with all our senses. So also not only acoustically, also visually, and it gives us some type of quality perception. So the acoustic comfort is also an important thing, and it relates how we feel acoustically about this room, or how a room is acoustically suitable for a certain application we would like to use it. So its reverberance, the spaciousness, the background noise, the speech intelligibility, this is all important. So this can be all designed, and so the room acoustics, which gives a direct connection to acoustic comfort, depends on certain elements. First is the room volume, the size of the room. But then again, not all rooms of the same volume would have the same acoustic feeling. So the room shape is also very important. And in the end, the acoustic characteristics of all the interior room surfaces. So all walls, ceiling, floor, but also all furniture, everything what is in the room and it interacts with the sound is important to have this whole room acoustics experience. And let's look into a very simple example, how the room interacts with the sound source. Here is a section view of this concert hall, Vatroslav-Lisinski. You are, most of you well known. And if we have a simulation of a sound spreading from the stage, then it hits certain surfaces, and of course we see here the reflections from the ceiling, which are quite special in their angles, since we would like to reach the audience as much as possible. So if you go a little bit back, you can actually in time see how certain elements at the ceiling are helping for the sound to reach certain parts of the audience, and after some time, when the sound starts to spread, we will have a more and more even distribution of these red little particles, which represent a sound, and with the intensity scale here. So with time, again, it will become much less intensive, and less actually sound pressure will be off because of this sound source that emitted one, I would say, strong sound, like some clap, for example. And this concept we often use when we do simulation and measurement in rooms, because we think about some source position here again for the same room at the stage, and one position at the audience. And then we look in this graph, which is called a reflectogram, where we see how the sound energy comes to this audience location where we put a microphone, and we measure in time how the sound energy reaches this position. So first we will have this red line, which represents the direct sound coming first to between the source at the stage and in the location of the microphone, and then more and more reflections. And with time, they will be becoming, as you see, a little bit less and less in amplitude, because the sound spreads. The inverse square law still is there, so the intensity will be lower. And again, with all reflections, there will be also some sound absorption occurring depending on the surface. So this is a very, for us, very useful type of thinking about this concept. So again, a very small demonstration. We can have a simple simulation of a room. We have a room source, sound source in green, and let's put anywhere a sound receiver. And then we start the simulation, and we can see in time how energy reaches this person, this is like a listener or a microphone, over time. So here we see the energy incoming in time, depending on all the reflections from the source. And as said before, we will start with the strongest energy of the direct sound, and then the reflections will come later on with lower sound intensity. So there will be lower sound pressure. Okay, so this is the concept also used in more elaborate simulations. This is just a simple one to make this concept more understandable. And here, just to go once again, so if you go it step by step, if you have a sound source like the loudspeaker here, a person listening to it, we will hear first the direct sound coming, for example, after 10 milliseconds, when the sound was emitted from the source at, let's say, 70 dB. And then if you put a hard wall, let's see like concrete wall, so we just have one reflection. We disregard here the reflection from the floor. Of course, there is always reflection from the floor, but for this case, let's say it doesn't exist. So we'll have another incoming sound at the person at the left after 2 milliseconds from the direct sound, and it will be about 68 dB, so lower in level. And if you put here a more absorptive surface, maybe a wall covered with some curtains, for example, then it will come in the same time at 12 milliseconds, but it will be lower in amplitude, like let's say 62, so even 6 decibel less than before. If we change this wall with a more scattering surface, so a rough surface, then it will be produce probably more reflections that will be able to reach this person on the left. So at different times, and we will have also different intensities. So somehow the energy that was emitted will scatter a little bit and come as multiple sources to this person. But if we have this wall put between the source and the listener, we'll not have the direct sound anymore, of course, because we don't have this visual communication, but we have this part of the sound that comes above the wall, as we heard before, and then it will come, for example, 1 millisecond later than the direct sound that is not existing anymore, and it's lower in amplitude, and if the wall is higher, then it will become coming later and being even less in amplitude. So all these are simple concepts that can be also a little bit oralized, so we can hear how these step-by-step reflections influence our perception of the sound source. So let's listen to these examples for a voice recording. First, listen it in a free field, so without any reflection.
Dobrodošli u Hrvatsku, u zemlju čija se bogata kultura.
Yeah, we make it very short. So let's put a hard reflective wall.
Dobrodošli u Hrvatsku, u zemlju čija se bogata kultura.
You hear the difference in the sound because we have one reflection that is influencing the sound color. If you put a soft absorbing wall like before, this is then the influence of the sound.
Dobrodošli u Hrvatsku, u zemlju čija se bogata kultura.
Less than before, but then the sound scattering wall.
Dobrodošli u Hrvatsku, u zemlju čija se bogata kulturna baština.
It's louder, yes, and it's different also in the sound color, in the timbre. If you put the sound barrier now, the sound sounds like this.
Dobrodošli u Hrvatsku, u zemlju čija se.
Or a high sound barrier.
Dobrodošli u Hrvatsku, u zemlju čija se bogata kulturna.
It's softer and less high frequencies. So just for comparison, again, the first one, the original one.
Dobrodošli u Hrvatsku.
Okay, so only one reflection, or for the scattering example, a couple of them do influence how we perceive the sound. So they're quite important also when thinking about how they influence our perception of sound. So we have these energy time curves, energy, the concept of graph where we see how the energy comes with time to the listener. And we have these early reflections coming, let's say the first 50 or 80 milliseconds, which are quite important for us because they support the localization, the clarity of the spoken word of the music, and then the late reflections that are more important by giving the influence about the room size. So it's like some reverberant tail. And the reverberant energy, as you see, and as I mentioned, does decrease with time because it spreads over larger areas, and we have this inverse square law. We have this absorption from the surfaces, as I said before, and air friction as well. So these three physical laws influence that the energy will fall in time in a room when measuring this type of graphs. Okay, and then we call this concept what we hear as reverberation in a room. Important also to say the sound field in the room is dependent also on the distance from the source. So, as you would expect, when we are in a general room and near a sound source, and when we go away from the source, we will experience this inverse square law. Well, the sounds will be roughly 60 dB lower when going to the double distance. But with larger distance, you will start to be more in the sound field produced by all the reflections that exist in the room, and these reflections form something called a reverberant field. And when you are far away from the source, by going even further away, usually the sound level will not change or not change much. So you could think about having these two parts of the sound field in the room, and of course some area in between. So in the near the source, we call it the direct field, where the sound source is key and which is most important because it's influencing our perception most. And then the far field, the reverberant field, where the reverberation part, the reverberant reflections do influence mostly our perception of the sound. Okay. And now let's go to room volume and room shape. As I said, these are very important concepts when talking about room and how we can design good rooms for good room acoustics. And room volumes directly influence the reverberation in the room. Why? Because the larger the room, the more time will it take for a sound to reflect from a wall and come back to, for example, us if we are listening to a sound source. So roughly by doubling the dimensions of the room, we'll have roughly 6 dB lower sound pressure level on a spot in a room. So these reflectograms start to stretch over time, and then it is somehow also to be expected. Then this sound will come later and be more reverberant. So here just an example without an audible part, just two pictures of the same choir singing in two very different places. So the room volume is quite different. They are very similar in types of surfaces of the walls, floor, and ceiling, quite hard, all of them, with some chairs or pews in the right picture in a church. But the volume in the right one is much larger, so the reverberation from the source is much larger. But if we go now with the same thought, thinking, we have also demonstration, sorry, of this concept. So let's see about having a small room and then a large room with a band playing. So here, for example, we have a group of musicians playing in a small room, roughly 100 cubic meters. So let's say a living room with reverberation time 0.7 seconds. Okay. And if we switch to a very large room, like a concert hall of 10,000 cubic meters, and of course it will be more reverberant because of the concept from before. So as you guess, it will sound different. Let's hear how. You hear it will be more reverberant, but since you are probably, like here in the simulation, further away from the source, it will be also less in volume than being in a living room with the same orchestra. So the room volume has a large influence on the acoustics. I told before also that room shape is also very important, actually essential for this room acoustics, since it influences not only the aesthetics, but also the acoustic performance of a room. So again, we have the same choir compared in two rooms of quite simple, similar volumes, but of very different shape. And on the right, it's a very old stone atrium of a, well, old town in Dubrovnik, where the sound will form completely different than on the left picture. So it will, again, without a sound example, influence how the sound can be experienced in both of those spaces. So room elements that are a part of the room shape affect this behavior. And we have to understand this principle more in detail to know how to do a proper design of the acoustics. So a couple of concepts connected to this room shape part. A very common design or a very common shape of concert halls, especially from the 19th century, but also later on, are shoebox shape, which are, as the word says, with parallel walls and parallel ceiling and floor. But of course, they can have different elements on the walls to help with the scattering, with absorption, etc. So the ceiling height actually defines the volume, because the higher the ceiling for the same area of the stage and the audience, we have a higher volume and a higher reverberation. So it will also influence the sound pressure level, because again, if it's a higher volume, it will be lower because the sound has to spread over a larger volume, and the reverberation time will be larger as said. So again, what is also important when thinking about shape is, we mentioned before, so we have sometimes convex or concave surfaces. For convex surfaces, they disperse sound energy or scatter them, and they help to have a more even sound distribution, which is very often important to us. By concave, as we saw, they just focus sound very often in so-called hot spots, where the place of the circumference of this curvature is. But then again, it's very important where you sit. If you are in this focus, you'll be probably happy because you'll hear the sound very well and very loud. But then this energy is spent for this space, and all other locations around you in the audience will not get the sound energy because it's spent for this one location. So then it's not a good concept if we would like to avoid this, of course. What else? Another thing is when we think about shape and the elements in the room, we have to think about distributing all the elements important to the acoustic design more evenly on all the surfaces if possible, since they will be more effective. For example, if you have absorptive materials, it will be much more effective if they are evenly spread than just on one surface, for example, on the ceiling. And I will show you later as one of the problems in some designs where this was not the case. So in general, we would like to have in a room more diffuse sound field, where sound hits all surfaces with equally probability. And then it's important to have somehow also the surfaces important to us for the acoustic design to be on these walls and ceiling. Okay, and just here is the last picture of this part about volume and shape. Again, some of the rooms that also combine concave elements on the ceiling with different type of walls of materials and shape. And as you would expect, the acoustics will be quite different in each of them. So you have to just think in beforehand, designing all these spaces, what will they use for, and how they will sound. So how to somehow make us understandable how this will be heard. is a thing of the parameters. But before coming to parameters in room acoustics, let's look one more concept regarding room shape, which is the problem of standing waves, which I mentioned before. So rooms can have also standing waves in certain conditions, which means that at certain place in the room, especially at low frequencies, you will have pronounced sound pressure increase, and in some it will be decreased or very low. So generally, this is what we would like to avoid. And here we have a measurement we have done in a rectangular classroom in 1/4 of the room. Now, when I play it back, the frequency increases, and we see at certain spots in this room how the sound pressure changes. And at certain frequencies, it's unfortunately not written there what's the frequency, you will see that the difference between the sound level at different spots in this room can be quite different, and the frequency, when it's higher, it's less pronounced these difference. But at lower frequencies, especially for starting, you can really see very distinct places of high and low sound pressure. So this is what room modes produce, and generally we can calculate them, especially for rectangular rooms, where we have actually a very simple equation where we use non-negative integer numbers and the room dimensions, length, width, and height, the speed of sound, and we can calculate at which frequencies you will get certain modes. And here, two examples of two modes at different for different frequencies, where you can see the spots where in the room you will have this high sound pressure level and where it will be very low. So modes, nodes, and antinodes. How to avoid them? Generally, we have some recommendations or criteria how to avoid strong room modes. And one of them is to have a certain ratio of the length height, width height, or length width, which is below some certain number, or in some area. Do you have actually very different recommendations? But one very strong recommendation would be not to have the integer number of this ratio. So you would not like to have a small room of the same width and same length, because then the room modes are more pronounced, especially for rectangular rooms. So these are some, again, design principles to avoid. As I said, why in small rooms? Because then the room modes are more audible. In larger rooms, there are lower frequencies, then luckily we don't have so much problems with them. Okay, so actually, I think it would be maybe nice to make now a pause of 15 minutes, and then we could continue with the second part of this lecture. But thank you. Pause. Okay. Yeah. Okay. Yes. We take a picture now. Yeah. Then maybe 1 second we have a picture of the group with a 3D camera. Yeah. Yeah. So. Okay, the guys didn't understand. Maybe it's better. Some people went outside before we start in the second to have everyone in the room. Okay. Yeah, possible. Okay. Then please be back in 1, 12, 13, and 1:15 here. Okay. So. Okay. It's like this is important, but from acoustics.
Eravamo tutti inizio delle misure. A te, tutti qua, non mi ricordo più che c'è un capisco qui, però sicuramente esatto. Non ti dicevo la remember that we have also to put picture on your website, so yeah, it's very boring. Could you go to the first page, not this one?
Yeah.
So that's for the picture. This is the 40, so remember 45.
Yeah, I know where I stopped.
So just the first.
Control Alt hide. Okay.
Good, perfect. So last maybe
Let's see. Okay.
also test poi also with the equipment when you want. Okay.
Yeah, able to have this thing and this.
Yeah. Oh,
Yeah.
yeah,
Oh,
fantastic.
yeah, yeah, yeah.
Everything.
Everything is ready.
Okay, so maybe they do something.
Now if you can just find
You
the
can
right spot.
try several picture, well, but not a problem. Yes. Right. Okay. But do you also see the screen of the projector?
It's
Maybe
very,
you're going late. Go far
Yeah.
a little bit.
Okay.
Just to try. Yeah, maybe.
problem is that now the screen is very bright.
Don't
Yeah.
worry. No.
No, the screen is wider, then I'm thinner. I'm happy with this. Otherwise, I never recognize myself on pictures.
If I do something like this, I should have one with the correctly exposed screen and one with you correctly exposed. and then-
Yeah, because it's too bright.
Yeah.
It's too bright, yeah.
That would just be one with the phone, so that I'm sure.
Or I can step on the other side, maybe.
Yes, maybe, yes.
No, maybe both of us, because we are in the same. It's otherwise too bright now. Yeah.
Yes, yes.
Okay, then I can do something
Yeah.
like this with the equipment and the poster, but not the screen.
Okay, that's good. Very good. Then we have to take a picture with all the students.
Yeah.
At least maybe also with Marco. One thing also with Marco and Kobe because we are
Because we're all lecturers.
Yes,
You're right,
yes,
you're
yes.
right.
So now our two are four and then we go to three.
Yeah. Okay. So let's see how many people are there.
Oh, 20, maybe 25, maybe more.
Oh, I didn't sign it.
You have to see.
Yeah.
I like to see.
Yeah.
Also, you understand?
That's a decent number, and more people said they will come to the second lecture. So I hope it will. It will grow. Yeah. We have actually 3 courses here. So they are from 3 years, but it's not their proper usual time. So in them it's so hard with the artists, they have all the time different projects, and then if you get half the number, usually the lectures we are having. Yeah.
Are they all?
Yes, this is all in the lab with music, so it's all different, well, topics in relevant. So you have this theoretical conductors, instrumentalists for different instruments, of all students of the music academy. Plus, we get a couple of people from our faculty that we also send from another group, electric engineering and computing. Because my former PhD student, he was here, he just has now a course on DJ. He's a DJ, so when people like to come and listen, okay, DJ, and then he makes some, well, how to say, ask them to come. This also will be interesting. So I think 3 or 4 are here from this course from my home.
Okay.
Also, this room is very nice. Yeah, it's a very nice place.
It's like the studio.
Will you make the picture now before the? Okay. Mm-hmm. Okay.
So we are going to take a picture 360 for our website. So please go look at the camera. Don't agree, you can turn your head off. Whatever you want. Okay, otherwise look at here because this will be the camera for you. Just stay here.
Okay.
Second one.
Perfect.
Thank you.
Okay, so we can continue. Resume. Okay. So welcome back. Let's see which acoustic elements we use in the acoustic design. We'll start with the sound absorbers, which usually help us to control the sound pressure level in the rooms. And it's important to mention that there is no one sound absorber or sound absorber type that is equally well in all audible frequency of interest. So we have to combine how they work. And let's go on with this concept to speak about these three types of absorbers. The first one are the porous absorbers, which are all materials that you can blow through air. So they are porous, they release air, and then there is this effect of friction of air molecules that help absorb sound. But then they are very much effective at high frequencies. So good examples are all mineral wool or glass wool blankets, then carpets, curtains, foam, acoustic foam, etc. And this is the blue curve, which shows that the absorption coefficient is very high at higher frequencies, but it depends on the thickness of the absorber and the placement, how well will it absorb sound at mid and low frequencies. Then you have membrane or panel absorbers. So they are thin membranes of any materials, not very heavy in weight, that will have like a mass spring system type of absorption, and it will be most effective at low frequencies, especially at the resonant frequency. And typical are gypsum boards, which are lightweight walls, and then they do absorb sound, but also some wooden pop panels or other panels mounted in front of a hard heavy surface. And finally, you have the third resonant or Helmholtz type of absorbers, which are most effective at mid frequencies, and you can really design where they will be most effective, and they use this Helmholtz principle with multiple opening or perforation on a panel to achieve a certain absorption. So here you see just a sketch of all three types, so poros that can be mounted on the hard surface, wall, ceiling, even floor, or with a certain air gap. Then you get better efficiency at lower frequencies. And then there could be this membrane absorber with or without porous material behind. With, you get a better efficiency again. And then these perforated panels, like a series of resonators, like Helmholtz resonators, and again they get better efficiency if they have this resonant material below or behind the panel, which is mounted in front of the hard surface. And an interesting picture could be also this one, where you can see how the percentage of perforation influences the efficiency of these absorbers. So if you have, for example, a panel of, let's say, mineral wool, there is no facing, let's say nothing is in front, you'll have a large absorption at high frequencies, and then at lower it will be falling down, the red curve. Then if you put in front of one panel with a lot of perforation, here is only 13%, it will help to a little bit more effective absorption at lower frequencies or mid frequencies. And then with the percentage of perforation of the panel going down, the efficiency at high frequencies will be less and less, but at low frequencies it will be more and more. But in the end, if there is no perforation at all, then it will be again be not that efficient at all frequencies, only at low frequencies. So actually there is a combination. Without going much further and into mathematics, the physical principle and formulas, how to get this, there is actually a nice way how to tune these absorbers to a certain frequency, which is very often needed for certain rooms. Then we go to acoustic diffusers, which are elements with mainly cause, or the mainly task is to scatter the sound in multiple directions. And we already said that we would like to distribute the sound more evenly. So we would like to decrease actually the sharpness or the amplitude of some reflections, especially early reflections that we would like to avoid many times. So this diffusion can be done by certain type of surfaces. We already mentioned curved surfaces, which are very often, especially in concert halls, as reflectors, but curved one above, for example, stages. Then we can have a nice balanced sound that is spread from the orchestra, from this reflective ceiling surface to the audience. And what is nice with them, that they preserve the phase of the reflected wave, which is again nice to hear and to experience. So they can be curved in one or two dimensions. So we have cylindrical or spherical curved surfaces. The other would be having some irregular geometric structures, like the walls, the side walls in the concert hall of Wacław Lisiński, you probably know, which have very large boxes of different shapes and sizes at the walls. And it's important to say this will be effective to diffuse the scatter sound, but depending on the size of these boxes. So if the boxes are very large in size, so it will be effective only at very low frequencies. But generally, this principle can be used in all types of dimensions. Of if we have some irregular structures of lower size, it will be scattering sound at lower frequency much better. So actually, the dimension of these boxes, let's say, or these elements, should be more than a quarter of the wavelength of the wave we would like to scatter, like a general principle. Then we can have periodic geometrical structures, so not irregular, but periodic. A good example could be actually some seatings in halls and concert halls or theaters, where they also behave like scattering patterns, and they can be regular in 2 or 1 dimension. So we have, but not only seats, of course, there can be many times some cylindrical patterns on walls that are used for sound scattering. And finally, we have these, let's call them mathematical diffusers, or diffusers that are really calculated before to make optimum diffusers, like in only here the QRD diffusers in 1 dimension, in the horizontal level only, and they have wooden elements of different depth that are pre-calculated by a specific formula, and they are very often used, for example, in control rooms, where we would like to avoid strong reflections from the back wall, producing a more sound field connected to larger rooms, not to have this feeling to be a very small room, which sometimes control rooms are. Okay, so now we have those elements, and let's see how they will interact, or how they will influence what I already mentioned before, something with the first parameter and the most common parameter in room acoustics, in which is called reverberation time. So as mentioned, the sound waves in a room travel in all directions and are reflected, at least partially, from all the surfaces. So we have many paths, and these are then can be seen, what we also saw in these energy time curves. And actually, we have to look into them to see how sound behaves at a certain spot. And with them, then we can draw certain patterns of, again, direct sound between the sound source in yellow here in this picture and the receiver in green, and we see it here, and then all possible paths which will connect those 2 dots after 1, 2, or even more reflections, and we then calculate the energy, and we see the energy decrease slope. So as we've known from before, the energy will decrease after this first direct sound. The easiest way how to measure it, maybe, or to experience it, is just to clap. And then we use our ears as a microphone, and then we listen to the response of the sound of the room, and hear actually this decay which we experience regularly. But then we can have some idea of the quality, or better to say, of the reverberance of the room we are in. So, as I said, we have multiple reflections of the sound field. And we actually prefer a diffuse sound field that will, in the room, reflect the sound wave in all directions equally, probably. And then when we record this, the sound pressure on a space over time, we will see what we can here call a decay curve of the sound energy after the sound signal stopped to emit the sound. So the reverberation time is actually the time required for the sound to decay in level for 60 dB. This is the simple explanation, or the simple definition, and it is again frequency dependent. So from this example, we have to calculate at frequencies of interest what is the reverberation time, and then we draw such curve, or we calculate them. So it's showed how much time it needs at each frequency for the sound for this room to decay for 60 dB. So this is the definition, and this is the most common parameter we use in room acoustics. Okay, as I said before, it is very much influenced by room volume, but also by the surface materials of all room surfaces plus furniture and everything what is in the room, plus air attenuation. So if you have a very simple simulation of a room with a reflective wall shown here, then we will have these reflection parts with these blue lines. But if we had replaced them by absorptive walls, they will absorb more of the reflective sound, and then we will have lower reflection in amplitude, and then the fall or the decay will be faster. Okay, so let's see in some demonstration of this reverberation time and how it influences specific rooms, first for speech and second for music. For speech, the typical room where speech intelligibility or speech communication is important are classrooms. So here one simple example of a classroom that has no absorption. It has a reverberation time which is, let's say, quite large. It's not written here, but maybe we can calculate it here. But listen to example for this classroom without an added absorption layer on the ceiling.
Johnson's work included calculating trajectories, launch windows, and emergency return pods for Project Mercury space flights, including those for astronauts Alan Shepard.
Okay. We mustn't listen too long. It's already clear. It's quite unintelligible. The reverberation time is too large for this type of room. So if we add 50% extra absorption on the ceiling, we will get a decrease of reverberation time, or we can listen to it and experience it like this.
Johnson's work included calculating trajectories, launch windows, and emergency return pods for Project Mercury space flights, Johnson's work included...
I guess it's clear. It's even better. It's a little bit better already, and we can use even more absorptive surface, like the whole ceiling, and then we get this simulation result.
Johnson's work included calculating trajectories, launch windows, and emergency return pods for Project Mercury space flights.
It is most intelligible from those three examples. So obviously, for this type of rooms where the intelligibility is important, it is important to control the sound field, because too much reverberation directly influences if we will hear clearly the sound or not. This is, let's say, for speech signal, but we can also think about reverberation and spaces for music, and this might be different. For example, if we have a simple shoebox type of room and have a reverberation time which is quite low, let's say 0.8 seconds for a, let's say, concert hall with a lot of absorption added, then some music, symphonic music could be experienced like this. Quite dry. You'd say dry. Somehow it lacks reverberation for this type of music. So if we would play this back in a more reverberant room, or the same room without this whole added reflection, absorption, we would get this type of experience. Okay, so this is a short example for music, but not all music will prefer a large reverberation time, or some it's always an optimum, of course, but larger than, for example, for speech. If you have amplified rock music, then a concert hall might be too reverberant again. So let's listen to the same room, but with amplified rock music. And again, with curtains or added absorption, like this. Okay, so in general, we would prefer to have lower reverberation time for this type of music. So it really depends what a room is intended for. And we have to think about this when talking about reverberation time. Just in short, the reverberation time can be also calculated. We have certain mathematical expressions that are used for this. We have like several formulas. The typical one is the Eyring formula, which is a common formula to calculate room reverberation time, or the Sabine formula for more reverberant rooms, where it's we can show it's quite simple. Actually, it depends on the room volume and on the absorption area, which is actually calculated as the average absorption coefficient on all the surfaces in the room. So if you know the absorption coefficient of all the surfaces in the room and the room volume, and of course all the surfaces, how large they are, we know everything to calculate the reverberation time of a room beforehand, which is important, of course. And then we can use either more complex methods, as I mentioned before, so software for simulating acoustics, or very simple for calculation using maybe simple Excel formulas where we define all the interior room surfaces. We have to know their absorptive coefficient, frequency dependent again, and then for each frequency, we can calculate from these numbers the reverberation time, and then we can draw this nice curve and say, okay, this is the predicted reverberation time of a room, knowing the surfaces, its volume, and the absorption coefficient on the frequencies we are interested in. Usually, we look at least between 125 Hertz in octave bands up to 4 kilohertz, or we can be a little bit extended, but these are the like must frequencies we cover when thinking about room acoustic simulation. We will listen much more in the next lecture about measurement in room acoustics. Here just an example that, of course, this can be also measured in different with different ways. There are different norms and standards that say how to do it. So more on this after I finish with this lecture on room acoustic basics. Okay, reverberation time is just the first parameter we use when talking about room acoustics and the quality of room acoustics, and if you compare rooms in objective way. And this is maybe also a problem that we use these parameters to be able to objectively compare different rooms, or to predict a room, how it will sound before it is built, by using all this knowledge gathered in all the history, and which is quite large in terms of acoustic measurements. But we need this common language even more between acousticians and musicians and the audience. So acousticians are mostly engineers, musicians are the people performing music, of course, and not engineers, and the audience is not musicians and not engineers. So everyone is experienced a room, but the common language is a problem if you have only sheer numbers, and it is a little bit problematic how to explain then to general audience all the parameters that exist and that are used when designing rooms. So again, generally we can say we have objective parameters and subjective parameters. Subjective are how people experience a certain aspect of room acoustics, and they give some marks on how they experience it, but objective are measured as reverberation time. I will not go into formulas here, just to mention a couple of them that are important for the room acoustics. So we can, for the objective parameters, look the audience parameters, important for the audience in, let's say, concert halls. And then there are specific stage parameters important for the musicians at the stage. So some of them. We have sound strength, which is a measure how much a room amplifies a sound, or not amplify maybe per se, but to know how much the local reflective surfaces at the stage will help project the sound energy towards the audience. And it depends very much about these reflectors that will help in sending a right amount of energy towards the audience, and then the strength parameter depends on this. And there are also different subtypes of this strength parameter. Then, besides reverberation time, there are some other reverberance measures, like the early decay time, which only shows how fast will the sound decay in the first 10 dB, but then projected to 60 dB fall, which is somehow more correlating how clearly we hear a certain sound and how good we will understand some speech. It's more than the reverberation time parameter. So there's some sub-variation of this reverberation time. Then there are a certain number of clarity parameters, which are, as the sound term says, about the clarity of music performance or speech. And then there is a certain ratio of energy in between the first 50 milliseconds and then the rest of the reverberation of the energy time curve, which we use to measure this ratio of energy, or the 80 milliseconds for music. So these will get some numbers that will be relevant to how clearly we will experience either music or speech in certain rooms. Then we have a group of spatial impression parameters, which is more connected to the way how we hear the sound. We hear it with 2 ears. 2 ears give us this so-called binaural hearing, which again helps us to experience the spatial part of the sound. So we are not listening only to mono music, but we do experience also the direction of the incoming reflections besides the direct sound. And there are measures that show us how much this spatial part will influence our perception of the spaciousness of a room. Then we have a tonal balance parameter group, where we look into the ratio of the low frequency to mid frequency energy, or the high frequency to mid frequency energy incoming to a certain place we are listening to. So again, if we have a large or larger bass ratio, it will give a warmth to the sound. And if it's this treble ratio, it will give more brilliance to the sound experience. Then we have intimacy parameters that show us how intimate we will experience some sound in a certain hall, because it shows the gap between the direct sound and the first reflections. And again, as I mentioned already before, we have these speech intelligibility parameters that are mostly important for rooms where there is communication, either one way or two way, but it's very important. So for all classrooms where it's important and key, we can understand persons speaking in a room. And again, a small demonstration where we can look how certain type of a room characterized by, like, let's say, some reverberation behavior of the room influences the room. So, for example, there is a room which has 1.9 second of reverberation time, but there is also some clarity, some gain parameters, but we can hear the difference in the sound response. And then we can better understand what all these parameters, for example, really mean when listening to a room. Otherwise, we are losing this connection between numbers, which are sheer numbers, and the experience of the room. So, for example, for this set of chosen parameters, we can listen to the example. And then I can choose a more strongly early reflection part and stronger reverberation. The reverberation time is the same, but we see that the clarity is much less. It was 4 dB before, now it's minus 4 dB. So how it influences our perception? So it's a different feel to it. And then when we know a lot much more of these examples, then we start to understand how all of these parameters, or at least some of them, do really influence a room. And then we can really start to use them in the design process of rooms. I mentioned stage parameters, and this is important because also the musicians at the stage have to hear themselves in orchestras, in choirs, for example. So it is quite important that for their performance that they are able to hear themselves clearly, not only that the sound they're producing is reaching the audience in a good way. So this is like also another part of the design process. So here just to mention them. And I also mentioned these subjective evaluation parameters that are used with real life persons sitting in halls and filling in some questionnaires, and then they think about different sound dimensions of the room in the room acoustics, about clarity, reverberation, spaciousness, intimacy, loudness. So some terms we are more familiar than with these numbers, and then we can say, for example, for a room, okay, I think it's very reverberant, just right, not enough reverberant, and then for each parameters we can make some subjective evaluation, and then it can be used, and it is used to somehow connect our feeling to the numbers we can measure with the acoustic measurements. Yes, so there is a link for each objective and subjective parameters, or we try to find it, better to say, and then we can have such overviews where we have a list of subjective parameters, a list of objective parameters, in what frequency range they are important for, and then we try to see how much each influences our perception of the certain aspect of room acoustic quality. So for the optimal acoustic design, what is important? So we heard already in some examples that, for example, for reverberation time, it should be somewhere expected, and some we prefer more than the others. So normally we would say for speech, it is important to be lower than for orchestral music, but again, it's also that it's frequency dependent. So for example, for orchestral music, we could allow not only more than for speech, but even more in the low frequency range than in the mid frequency range, for example. So we have to think about frequency dependence and then the optimal value. So we can find different type of recommendations in different literature about how much the optimum reverberation time is, depending, usually we draw it by room volume, but then there is no frequency. We look this for the mid frequency, let's say for 500 to 1000 hertz range. And then we, for a room of certain size, let's say an auditorium should have a reverberation time for example, 0.7 seconds, but for a concert hall of the same size, it should be 1.2. So someone had this already measured with subjective and objective waves to have these type of recommendations, which is very useful to us when we would like to make a good design of a room of certain use, depending again of its volume and application. And here, for example, a German norm, 18041, where you have, again, this distinction between different type of program that will be used in a certain room, depending on the volume. And you have here also a certain tolerance for the reverberation time, which is like a reference one at mid frequencies. And then you can see how much it can divert from this reference value at lower and higher frequencies, since this is actually the job of an acoustician, to find the certain materials that can be used to get here for the reverberation time in the optimal range. And we can see here also one nice example how a certain deviation from the optimum will influence our perception of the room, which is also quite important to know this beforehand. So, for example, if you have an optimum reverberation time, and optimum sound strength, which is from some, let's say, recommendation, we get it. And if we will have an increase of volume, the reverberation time will be starting to be muddy. our perception of sound with because we will be above this range, but below it will be too dry. In the same time, if we will go above with the strength, it will be too loud. In the other the dimension or the other direction, we have a 2 weeks perception of sound in this room. With increasing absorption, we see how the trend also will change. It will go in this direction for increasing volume in this direction. So we can think about different combination of parameters that will influence not only one aspect of sound. It always affects everything. So every change in the room will affect everything. But we should somehow have this experience and the knowledge how it will affect everything important to us. And this is like a multidimensional space of possibilities that should be explored when thinking about an optimal acoustic design. Which brings me to my last part of this lecture, and these are the typical defects found in many examples in the room acoustics part. And some are more severe than the others, but unfortunately, most of them we can see in experience, which means they are not avoided always. And I will show you 3 examples, all the 7 of them. So first, we would like to have a room without an echo, and an echo will occur when a reflection will come after the direct sound very late, about 50 milliseconds or later after the direct sound, which is translated to a path of the reflection about 17 meters. So if you have a wall very far away, maybe about 9 meters, the sound will reflect, it can come too late and can be experienced as an echo. And here, a very unusual place to find an echo was actually in a project where we had to measure or to optimize some sound system for a cinema festival in Pula, in this antique theater. And when we did the simulation and the energy time curve, we could, of course, oralize it. And when we oralized it, we heard this type of impulse response measurement. So let's listen to it. I hope you could hear this distinct tak-tak. So you heard the echo. The echo shouldn't be there because above is only the sky. And there are no walls. There's just some stone elements left in this theater, but they are wide enough, obviously, to produce this type of echo. So in the real theater, when we did the same measurements, we got the following sound. Okay, so a little bit different in sound color, but you still don't hear only tak, but the longer tail and some echo that could be distinct. So obviously, this is, although maybe surprising, acoustically a problematic space because you will get echoes from these very far away stony pillars that are remaining of this theater. And this is very rarely. We have much more problems with long delayed reflections, producing not echoes, but these long reflections that will influence the quality of, for example, speech intelligibility. So a nice example is, again, a church here in Zagreb that has interior surfaces exclusively built from concave walls. There are no straight walls in this church. So the reverberation in this, when it was done and already used, was very long. So it sounded like this. So it's a measurement of the reverberation time, like impulse response initially. It was about 13 seconds, something like this, I think. And then with some renovation that were allowed by the architect that was still making the certain limitations what can be done, it was half the number, so about 6.5 seconds after renovation. Okay, which is still too much, but this is what could be done at that time. Okay, so this will for sure influence the intelligibility of speech, and this was the reason why this project was done. Another typical defect are shadow zones in rooms, which are typical for rooms with balconies or theaters, where below theaters you don't get the nice reflections from the ceiling to reach audience below balconies. And here we have again our concert hall, Bartosz Lisinski, that doesn't have a balcony, but it had this Eurosong contest in 1989. And then they built in this area a long corridor for reporters that had, or translators, which were sitting like in this area, which was put in the room. And the problem was that reflections from the stage arriving over the filming reflections to this area were reflected also from this corridor and didn't reach the last few rows anymore. So it was they saw that the visitors stopped buying tickets for the last 2 or 3 rows because the sound experience was much worse than before and not feeling like you are really in a hall. And then after a couple of years, they removed this. So to get these, again, last few rows, the same acoustics as the rest of the hall. And then afterwards, it was really again, better in terms of not having these shadow zones, not having zones where you don't reach with the reflections you are intended to do. Okay, the next one, and the important one, is the focusing effect. And the focusing effect, as we heard few times before now, until now, is because of the concave surfaces very often. So on the left, there is they tried for a festival of small choirs to make a nice reflection element that would help the singers. But when they build it, just having this concept in mind that some reflections would be nice, and they liked this shell type structure, they saw that it was not doing what was intended because they didn't calculate this focusing that was occurring very strongly. So some choir members could hear the others very well, but the others beside them didn't hear it at all. So it was not helping them at all because they didn't calculate where the focus point is. And here's another example of a chapel, a very modern one here in Zagreb, where they built it like a cone. And this cone, if you're in the center, this is a simulation, is reflecting the sound multiple times through the middle, producing a very strange effect and acoustically very problematic. It's not, it's annoying, I would say. So here just it's the worst part of focusing you could make almost in one room and putting it into use. So some focusing, as mentioned also here, is not favorable. Then we have flutter echo. Flutter echo is an echo that repeats many times in a short period of time because there are parallel surfaces that produce this pattern. And we have this pavilion here in Zagreb, again, in the Maksimir Park, where you can be inside, and if you clap, then you can record this type of sound. So this is typical flutter echo. I'm quite sure that the architect didn't intend this in the 19th century to make a flutter echo pavilion, but it is a nice addition to a place where people like to come, and also children, and to clap inside, etc. But then it's a problem if you build, for example, or make a renovation of a small multimedia or multifunctional hall in a small town near Zagreb, where there are 2 very distinct places acoustically on the stage. The green part is inside this stage where there's a lot of curtains, very damped sound inside because all the acoustic absorption. And then you have 2 meters in front in this proscenium part where you are in front of these curtains, and you have side walls that give you some better reflections. But if you burst a balloon at the place here indicated by the green or yellow arrow, you will have different sound. So for the green one, you can listen now to it. Okay, this is in the damped part, and the yellow one. So it's maybe better audio by headphones, but you hear a flutter echo. It's not long, but it's completely different than in the green part. And then, of course, as a suggestion would be always to put some sound diffusers. And the funny part is these sound diffusers were actually bought and installed, but not at the ear level where you would expect them to be efficient, but above. So the easy solution would be just put them down and you are solved, at least the flutter echo part. What else? I spoke about scattering, and this is an example of a sports hall that was built for a world champion in handball, another town here in Croatia, where they put the whole absorption on the ceiling, very absorptive area. So all absorbing panels, but you have parallel walls at the field, which means that the sound energy will really circulate or being reflected in this horizontal plane. There is no diffusion almost at this wall, so it will not reach the upper part equally probable. So the reverberation time is much larger than if this absorption would be scattered or put equally also on the walls. And this was, for example, the problem to get too high reverberation time because of this not ideal placement of absorptive elements. And this final example shows what if there is too much scattering. So here is an example of a room that is also a multifunctional room in Split, where it's used, or it was used at least once for this festival of choirs. And when you have this large problem of this cassette type of ceiling without any real I would say you don't have the sound distribution with flat or with a curved reflector. So you get reflection all over the place. And if you went to the audience, at some places it was fine, at some it was very strangely the sound coming from. So one of the solution, or the only solution found, was that the choir step a few steps before and to sing near to the audience, because you don't get the support of the ceiling you would expect in halls where it's important. And where if you have some music performance, then you have to really have this also reflective part calculated, and not to have one that is random. And this example, it was less than ideal. And I think, yeah, this is the last slide. So herewith I will conclude my presentation, my lecture, and thank you for your attention. And we make another pause of maybe a quarter an hour before starting with the next one. So thank you for your attendance. Okay, and me.